we have the statistical mechanical background, and we wish to make one more step and asking how that knowledge is going to help us to understand the rate of an elementary chemical reaction. To start, we'll examine the collision theory. We said that elementary reactions are a result of molecular collision. Upper molecular collision between two reactants, you could find a reaction, or it may just bounce back. So for an arbitrary chemical reaction having reactants A and B and products C and D, the reaction rate is essentially given by collision rate multiplied by a reaction probability. All right. So let's examine the collision rate first. All right, assuming for now reaction probability is unity. Anytime two molecules collide with each other, something will happen to them, leading to some products. For collision, limiting case, if I have a molecule A and a molecule B, we shall assume these molecules are spheres, just to simplify the problem. And the diameter, rather the collision diameter of the A molecule is sigma A, and that of B is sigma B. You have head-on collision, or you can have off-center collision. Limiting condition for the off-center collision is when A and B traveling relative to each other barely kiss each other. Okay? This last scenario of a collision sets a collision cross-section. And any trajectory of the two molecules flying within this collision cross-section would have undergo collision. The radius of this collision cross-section is sigma A plus sigma B divided by 2. And therefore, the collision cross-section of pi r squared is given by the mean of the collision cross-section of individual collision diameter of the individual reactant divided by 2 squared multiplied by pi. And then I have a volume given in this cube. In this cube, I place NB and sub B number of B molecule. I shall have one A molecule flying through this volume at a mean velocity equal to V sub A. I'm asking over unit time, how many B molecules does this A molecule will swipe through? Okay? So if you look at one A molecule sweeping through a cylinder in which you find NB molecule, but this NB molecule occupies the entire volume, then the frequency of collision is equal to the cross-section. Okay, that's an area. Multiplied by the mean velocity of A, that's the volume rate at which A molecules sweep through. And if I have NB number of molecule within this volume, over, of course, a concentration or density, then volume cancel out. So this would be number of B molecule I strike per unit time. All right? Now, instead of having one A molecule, I have NA number of A molecule. Then the total collision rate would be number of collision per unit of volume per unit time is this expression multiplied by the number density of A molecule. Is that clear? Then this NA over V is the number concentration of A, number concentration of B. This group is effectively the collision rate constant. After all, this expression must be consistent with the rate law. Rate of chemical reaction is proportional to a rate constant multiplied by number density or concentration of A and the concentration of B. Alrighty? So this is the collision rate constant, in which you find a mean velocity of relative motion between A and B. we start from the mean velocity of a gas molecule, and that's given by some volume distribution, velocity distribution, multiplied by velocity itself, integrated over all velocity possible. And in my lecture notes on page 3 to 5 of lecture 4 note, you will see the derivation. The mean velocity of a gas is square root of 8 kT over pi m. And if you plug in the value for m, typically for example, nitrogen, and if you plug in 300 Kelvin, you'll find this value, as evaluated by this equation, is about 300-400 meters per second. That's related to sonic velocity, sound speed. Okay. Now, since I have relative motion, and as far as relative motion is concerned, the relative velocity is square root of two individual velocities squared. Plugging that expression, pulling out square root of 8 kT over pi, you're left with 1 over ma plus 1 over mb. That combined together is 1 over reduced mass. So reduced mass is defined as 1 over mu is equal to 1 over ma plus 1 over mb. Yeah, please.
Is that assuming a Maxwellian distribution?
That is to assume Maxwellian distribution. And in the derivation, we start from the Boltzmann energy distribution, recast this energy distribution in terms of velocity distribution, involving a transformation from kinetic energy to momentum. Okay. The question is this based on Boltzmann energy distribution? The answer is yes. Okay. And this is the classical equation governing the velocity of relative motion between A and B, in which if you have relative motion, the absolute mass is replaced by the reduced mass. The reduced mass in physical essence is to say that it's dictated by the faster moving molecule of the pair. Imagine if you have a very light molecule, like a hydrogen atom, striking into a heavy molecule, let's say benzene. And from this equation, you realize hydrogen atom would move about in a space faster than a benzene molecule, despite the fact that kinetic energy is the same. Hydrogen has to move faster in order to make its own kinetic energy equal, the same as a heavy molecule. So therefore, the mean velocity, the relative mean velocity is dictated by the small molecule, not the larger one, or the lighter molecule, not the larger one. This is just like you go to a schoolyard. The relative velocity for me running around the children is not dictated by my velocity, but dictated by the children's velocity because they can run faster than me. All right? That's what the physical significance of this reduced mass. Taking an example, if I take a hydrogen atom reacting with O2, I ask the question, what would be the collision rate? I take the collision diameter of hydrogen, which I'll talk about shortly, to be 2 angstrom, and that of oxygen to be 3.646 angstrom, such that the mean collision diameter would be 2.755. Plug in those values plus the reduced mass into the collision rate constant. Plug in the temperature. What I found is that at 300 Kelvin, the collision rate constant is of the order of 10 to the 14 in the units of cc per mole per second. Okay, let's go over the example one more time. If I take the reaction or the collision between the H atom and O2, I'll use the value for the collision diameter around 2 angstrom for hydrogen, 3.5 angstrom for oxygen, leading to a mean collision diameter of 2.7. I use the reduced mass based on 1 for hydrogen atom, 32 for oxygen. And you divide it by the Avogadro number gives you the exact mass. Okay? Plug those two values into the collision rate constant expression. Plug in the value for temperature. What I have is at 300 Kelvin, the collision rate constant is of the order of 10 to the 14 in a unit of cc per mole per second. That sets the upper bound for any rate constant of bimolecular reaction. 10 to the 14. That's where it's coming from. All right? I don't know if you have this experience. Sometimes you take a reaction mechanism, you run it, and with chemical code, it was difficult for you to obtain a convergent solution. How many of you have run into this problem? You have. Quite many. And then in numerical world, this problem is known as the problem, as far as differential equation is concerned, is stiff. Stiff means that you have some very fast process, you have many slow process. And in order to do the integration, you have to integrate over the past process. Your time step size is determined by the fast process. This disparity in rates that can vary by many, many orders of magnitude, making a time step ultra small, okay? And leading to non-convergence or difficult in convergent problem. Do you know where that problem comes from? I always say that nature is never stiff. For a stiff nature problem, you're going to see physical phenomena that becomes, for lack of a word, weird. Often when you run into this problem, it's because this reaction mechanism or model, usually very long, would have rate constant that are very unreasonably assumed, usually in the form of exceeding the collision limit. So take one suggestion next time if you were to use a reaction model doing a particular simulation. The first thing you want to do, as I always do, is to calculate the rate constants over the range of a temperature of interest for each and every reaction in the model. When you have more than 1% of the reaction having rate constant exceeding this type of limit, physically, it's a bad model. Okay? For that, this reaction probability can never be larger than unity. So if the collision rate and therefore the collision rate constant exceeded this theoretical value, it's a bad model. Where do this bad rate parameter come from? Carelessness in how we evaluate the rate parameters. Or sometimes due to the Arrhenius law, measurements are only done at a very high temperature, and over many order of magnitude, when you extrapolate to low temperature, you could get orders of magnitude off in the rate parameter. The result is that you have, if you run a flame problem, you have artificial radical sink that pull the radical from the flame on the cold boundary. That's artificial radical quenching on the surface. When a flame cold cannot converge, usually that is the problem. Is you are inventing physics that nature does not have. Okay? Stiffness problem is usually a problem with model, not having to do with numerics. Numerics, in my opinion, in my experience. All right. Now, so far we've talked about the rigid body collision. These are two billiard balls. They don't interact with each other, except when they started to touch each other. Your potential energy shoots to infinity, so therefore they must bounce back. Molecules are not billiard balls. Molecules are made of charged particles. They shall interact. They shall interact before they touch each other. And we've learned this earlier, that this interaction is usually governed by, is expressed by the Lennard-Jones or van der Waals interaction, expressed as a function of separation distance. In the long range, when two molecules are far apart, we make that to be our reference energy, that's 0. Putting the molecules closer to each other, you have nucleus interacting with the electron, and therefore leading to a positive attractive force. Thus, potential energy must go down, because as the two particles are attracting each other, your kinetic energy must rise. Total energy is conserved, so that the sum of the kinetic energy and the potential energy is still constant. Short range is because electron in one molecule started to merge into the other molecule, leading to electron-electron repulsion. Therefore, you have the potential energy shoots to the roof. A rigid body collision essentially does not account for this well. This potential function would look like a flat line until they hit each other and goes to infinity. All right. Origin of this type of force comes from dipole-dipole interaction. For example, in a water molecule, oxygen side is slightly electron rich. Hydrogen side is slightly electron deficient. So this leads to a polar molecule. So when two water molecules interact with each other, there is a preferred orientation. Okay, you have OHH. Then the other water molecule knows it wants to flip around having hydrogen here, just that it can interact between the slightly electron-rich oxygen with the two hydrogen, which is electron deficient. You could have a water interacting with, for example, nitrogen, which is otherwise has no dipole. But because of water is polar, it can induce the dipole in nitrogen. All right? That's called a dipole-induced dipole. The third effect is due to electron oscillation. It's a dynamic effect. I have two atoms, electrons are wandering about, and therefore, over time, they oscillate back and forth. The next atom or molecule sees it, it will oscillate its electron in sync, again, because of electron interactions. That's called van der Waals interaction or dispersion interaction. Van der Waals interaction in general refers to all three types of interactions, all grouped into a Lennard-Jones 12-6 potential. These are non-bounding potential. Non-bounding, not considering how a bond form and a break. Those are long-range interaction than a bond forming and breaking process. This potential says that given this form, this is r to the power of 6 dependency. And in the repulsive part, it's r to the 12th dependency. It's very steep. Okay? This equation is empirical. This equation allows us to fit many experimental data. Therefore, all the sigmas that I discussed earlier comes from this potential. All right? Epsilon is the well depth here. All right. And if you look at this property we talked about the other day, this is kind of a table you find in the ChemKing transport data package. My apologies, somehow my epsilon became E, my sigma became S. Anyhow, in general, the value for sigma varies with the size of the molecule. Hydrogen atom, for example, is about a 2 angstrom. Methane is about 4, and CO2 is about 4, and benzene is slightly larger. Epsilon value usually expressed as epsilon divided by Boltzmann constant, so that its unit is Kelvin. Okay? And it varies from something that's small to something that's large. And all these values will come from bulk properties like viscosity, like diffusivity. It's backfitted through the Chapman-Enskog equation. All right. Okay, non-rigid body collision and its effect. If you put non-rigid body involved in this interaction, then at a low temperature, because of attractive force, the B molecule would see A molecule to be slightly larger than it should be. This is just like without a gravity, a comet would fly by the Earth, following a straight line. But because of gravity, the Earth is able to pull the comet in, so from the comet standpoint, the Earth looks bigger than it actually is, because of that force of interaction. Okay? This force of interaction can also make the apparent collision diameter smaller. That happens at a high kinetic energy. The pulling in and swing by, the flyby, okay, leading to effects that reduce the collision integral. So in this case of hydrogen and oxygen, at low temperature, this is about 1.1. It's a correction term on the effective collision, on the collision cross-section. It should be understood as such. And at a low temperature, it increases this cross-section by 10%. At high temperature, it could as if this cross-section is reduced by about 10%. So it's a very small correction. Sometimes it's important, other times it's not. Now those are all non-binding interactions, not involving formation of a covalent bond or breaking of a covalent bond. Next topic is now let's talk about a chemical reaction. Chemical reaction is about making and breaking a chemical bond. The simplest chemical reaction, or one of the simplest chemical reaction, is the reaction between hydrogen, H2, and its cousin, deuterium, its isotope. The only difference between deuterium and hydrogen is that deuterium has one more proton in its nucleus. It's twice heavier. It's twice heavier, it's twice heavier. Okay? Electronically, they're identical. The only reason we use deuterium is because it helps us to label things. So otherwise, I could do this reaction as H2 plus H, except for your products would be identical. All right, let me ask you one question. If I carry out the reaction of deuterium and hydrogen at equilibrium, would I get more HD or would I have more H2 remain? The energy, everything else is identical, is the same. What is different? Their symmetry number. H2 has a symmetry number of 2. HD has a symmetry number of 1. Okay? Therefore, entropy differ between HD and H2 by exactly gas constant times ln 2, with the HD entropy being larger. Therefore, if you measure the equilibrium composition, you will find twice more HD than H2, just because of this entropy difference. This reaction is, again, another example driven entirely by entropy. For that, enthalpy-wise, they are identical. Okay? Now, let's look at this reaction. Okay? And this reaction requires it to overcome some kind of energy barrier, or it has to play on some kind of a complicated potential energy surface. All right. Let's look at this chart. This chart is a plot of potential energy versus two independent coordinates of the molecular system. This is the HD distance. This is HH distance. Okay? So the reaction occurs because if this is H2. I have a deuterium come in, knocking on the hydrogen on your left-hand side. Then by spring action, knocking out the hydrogen atom on the other side. And you know this thing, desktop playing toy that having like a balls with on a string you're gonna go. It's more or less like that game. Okay? One comes in, kick out of the other. And of course, you have two coordinates you need to worry about. All right? One is HH distance, this is HD distance. All right? As D comes in, HH distance enlarge. So as I decrease the HD distance that's over here, I'm marching in this direction, the HH distance must increase. So the reaction occurs by following somewhere along this valley. All right? But this valley, the reaction does not have to occur just directly marching on this valley. It can swing around. This is just like a complicated bowling alley. It's not a flat, it's curled around this. You throw a ball down the line, the ball has to go over the hill, go to the other side. But in doing that, during the process, it's also going oscillation left and right. Okay. The left and right motion is basically symmetric stretch. I'll show you this. And the reaction process is basically asymmetric stretch. Remember, if this is H, this is H, this is D. In a 3-atom system, I can have symmetric stretch, right? This symmetric stretch is not doing anything, not helping the reaction process. This process does. When D comes in, the other H pops out. Okay? So you have two independent coordinates. This motion is this going orthogonal to the valley. But this motion is what marching along this path. And of course, if it does this, it just goes back and forth at it. But if D comes in, really kick the hydrogen out, you'll be marching straight, turn the corner, go that way. Is that all clear? That's the nature of chemical reaction. So as you walk along this path, you look left, it's high heels. You look right, it's also high heels. You look at the back, going downhill. You look up, you look at the front, it goes up. Until it comes to this particular point. You say, oh, the front starts to go downhill. On the back, it's also going downhill. So at that point, the nature of this potential energy surface looks like a saddle point. A saddle point is one that in 2 dimensions, in one particular dimension, looking left and right, it's going downhill. The front and the back goes up. Is that clear? So the critical point is this saddle point. It's the energy on this saddle point the reaction must overcome. You must get to the saddle point before reaction can occur. If I project this potential energy into some kind of contour diagram, it would look like this. So this is a projection of the 3-dimensional surface on the 2-dimensional chart. And the red means high potential energy. The blue represents low potential energy. So reaction is about marching along this line until come to this X dash. X dash is the saddle point. It's a critical geometry you must overcome. As if you're rolling a ball up on a hill, and if you cannot pass through this point, then the ball has to roll back. You try this one more time. Once you pass this point, it must go downhill on the other side. There's a point of no return. This critical point or this line is known as the dividing surface. You make it or you don't make it. If you make it, reaction occurs. If you don't make it, the 2 reactants will fly apart with no reaction. All clear? So that one is a zoom-in version of this region, except to say this valley is quite narrow in general. Okay? In such a way that I can define a reaction coordinate, transforming this type of potential energy into a reaction coordinate. This reaction coordinate is the lowest energy path for the reaction to occur. Any other path will require high energy in all or parts of this potential process, That leads to a simplified diagram. If I were to just follow this reaction coordinate, that is the minimum energy path, I get this bluish line. But that's electronic energy. You have to consider the 0-point energy. Adding on top of it, H2 has a 1 vibrational degree of freedom. Therefore, it has its own 0-point energy. That's given as this point, or this line. HD is on the other end. This is the product. and it has identical electronic energy just because deuterium is basically hydrogen, except it's twice heavier. That doesn't impact how electrons move about. And overall, you must pass one particular saddle or critical geometry point. At this point, you have a complex. This complex is denoted as HHD. The dagger usually represents something critical. That itself has 0 point. So the effective potential energy path is this dashed line. Already? That includes the 0 point. Now, between the 0 point of the reactant to the 0 point energy of this critical geometry, we have something called energy barrier. That's the very rigorous definition for what energy barrier is. Because this reaction have identical electronic structure in the reactant, it's thermally neutral. It's neither endothermic nor exothermic. So as far as potential energy is concerned, these two are the same. If I were to generalize to arbitrary reaction, I talked about this already. Okay. Something that I did not talk about is you can view this reaction, of course, in a forward direction, leading to a forward reaction energy barrier. You can look at this reaction from the back end. Of course, you have a back reaction energy barrier. In this case, they are identical. Already? And the reaction enthalpy is basically at 0 Kelvin, is the 0 point energy to this 0 point energy difference. And you take them together, it must be equal to 0. It's a thermoneutral reaction. To generalize to an arbitrary reaction, this reaction can be endothermic or it can be exothermic, as I will show you. If you take AB plus C forming some sort of a complex at the top of the hill and come down to the products, you have a forward energy barrier, you have a back energy barrier. Then the difference between the two is enthalpy of reaction. Is that clear? All right. So the forward and back reaction energy barrier are related by the enthalpy of reaction at 0 Kelvin. Why 0 Kelvin here is because I'm counting from 0 point energy. I'm not worrying about any vibrational excitation at a finite temperature. 0 Kelvin, that's the base energy you can play with. Exothermic reaction, of course, differ in this diagram only in the relative position for the potential energy between the reactants and the product. You flip this around, this equation still applies. You have the forward energy barrier, you have the back energy barrier. In this case, the enthalpy of reaction becomes negative. So that take the back reaction, subtracted by this difference here, you get a forward energy barrier. All right. Any questions about this? All right, this is really, apologize for almost the end of the day, bore you with that many equations, but this is not, should be quite obvious. So let's take a look of the relationship between rate parameter. Mostly reaction, well, Arrhenius law expression, relating various properties in this parameters in this expression to the potential energy surface that we just discussed. What you find is from microscopic reversibility, that's another way of saying if I use equilibrium constant. The equilibrium constant is K forward divided by K backward. Plug in the Arrhenius expression, it becomes A sub F divided by A sub B. Then you have the forward activation energy and the back activation energy in exponential term. Okay? From equilibrium constant definition itself, in this case, Kc is equal to Kp. And that's Gibbs free energy of the reaction. Split Gibbs free energy of reaction into enthalpy contribution and entropy contribution. You split this expression into two separate terms. You compare this expression with that expression. What did you find? What you find is the A factor and activation energy of a reaction are each related to two different thermodynamic properties, in that the ratio of the forward A factor to the back A factor is related to entropy of reaction. And then the activation energy difference, that's this term, don't worry about this whole math here, is to show you these are all the sensible enthalpy correction. At the end, the activation energy difference is basically related to the enthalpy of reaction, with some small correction due to sensible enthalpy. All right. With that, of course, you know entropy is a function of temperature. And enthalpy, because of a sensible enthalpy correction, activation energy is also a function of temperature. It's for that reason that the Arrhenius expression is only proximate, in that both A and E are both temperature dependent, and they should be. All right. That just shows the limitation of the Arrhenius law. Okay. At the end, if you split this equation, what you find is activation energy relating to what the knowledge we learned earlier, the relationship between those energy barrier with the enthalpy of reaction. We found that activation energy is closely related to energy barrier, but it's not exact because of you need to worry about this sensible enthalpy correction. All right. All right. I promise there's a couple more I'll bore you, then we go we have the, what do we have tonight? Reception, right? Or farewell. We'll go party after this talk. Potential energy and vibration. Now, I talked about this a little bit. Taking that reaction with deuterium interacting with H2, we learned earlier that if we consider this thing to be linear, doesn't have to be linear. When deuterium attacks the H2 molecule, it does not have to come in a collinear fashion. But let's take this limit as such that my critical geometry is indeed linear. Any bending would give you high energy, thus off minimum energy path. And I have the symmetric stretch contribute nothing to reaction. I have two bending modes. They don't contribute to the reaction. The two bending modes plus one symmetric stretch are those, well, wiggly thing left and right as you march up on this potential energy surface, okay, along the valley. This motion is in fact related to the motion along the valley. Okay, we're talking about the asymmetric stretch. So that's my reaction coordinate. As you see now, chemical reaction about bond making and breaking is intimately related to vibration. As a matter of fact, they're not any different. It's a peculiar type of vibration that leads to chemical reaction or bond making and bond breaking. Then, if you look at the forces, the force is equal to the negative of the potential energy, derivative of potential energy with respect to spatial coordinate. By Hooke's law, this is some sort of a constant multiplied by displacement. This displacement may be understood as some arbitrary distance of the two group of reactants subtracted by a characteristic distance. This can be the equilibrium distance. This can be distance exactly on the top of this potential energy one. So it's a relative coordinate. Then the potential energy after integrate this is a half times kx squared, or the force constant is basically the second derivative of the potential energy. Now, one point I want to make, this is a local minima. This is a local maxima. This local maxima is associated with the critical geometry because it's on the top having one coordinate. That's the maximum. Along every other coordinate of motion, it's the minimum. Okay? then if you just interrogate that particular potential energy, we found that the vibration frequency for a local minima around this one, going back and forth, is proportional to basically the second derivative of the potential function, but it's a square root of it. Now, if you look at this particular, this local minima, your dv dx is 0, but the second derivative is positive, correct? I'm running from a negative derivative to a positive derivative going through 0. The second derivative is positive, so this square root is a positive value. So any local minima leads to a positive, real vibrational frequency. Then let's look at the nature of that transition state. That's the local maxima. The vibrational frequency equation stays identical, except for this second derivative in potential energy is negative. So square root of it gives us an imaginary frequency. The point, to takeaway point, is that any point of a saddle point of a critical geometry of the point the reaction must pass through in order to get to the other end of the potential energy surface, namely completion of a reaction must pass through this imaginary vibration sort of thing. All right. That physical significance will become clear tomorrow when we do the exact derivation to show that a chemical reaction is nothing more but a vibrational degree of freedom, particular one, along this reaction coordinate, got transformed into a translational motion. What I'm doing, looking at this, initially I'm doing asymmetric stretch, back and forth. But if this guy yanked me a little harder, I have to push that atom out. So that becomes a translational motion. Correct? That's the nature of a chemical reaction as defined by the transition state theory, a principle we will discuss tomorrow. You have a question?
Yeah, sorry, real quick, I don't know. What the hell is an imaginary vibration physically?
It doesn't exist. That is a translational motion.
So it means it just tunnels through that?
Well, this is like a grandpa clock. Okay? I can do this motion. Okay? The frequency is real and positive. There is one. Yeah, I have this motion. The frequency is imaginary because I'm going to have to flip over. That's a translational motion. Does that make sense? All right. All right, thank you guys for putting up with me. And we will continue tomorrow. Thank you very much.